This is Malborn Castle. It has stood for over 7 centuries. Exposed to storms, frost, heat, and endless time, it still stands with confidence. Now compare it to a modern brick building barely a few decades old. Both are made of brick, both have faced weather, yet one endures while the other slowly collapses. That contrast haunted me. How can ancient structures survive hundreds of years longer than buildings made with modern engineering? The explanation isn't a forgotten ingredient or a hidden medieval formula. It's something far deeper and far more uncomfortable about how we build today. Medieval builders understood a fundamental truth that modern construction has almost completely ignored. Buildings are not lifeless objects. They behave like living systems. They move, they breathe, they adjust. They repair themselves over time. Evidence surrounds us. Castles that are 700 years old still stand proud, while buildings less than 30 years old already show severe decay. Today, we're going to reveal the core flaw hidden inside modern brick construction. We'll uncover how Portland cement is silently destroying masonry from within, and we'll explore the medieval method that created structures meant to last 1,000 years. By the end of this, you won't look at a brick wall the same way again. You'll see either something destined to fail, or something built to endure, depending entirely on when it was made. Before continuing, think about this for a moment. What is the oldest brick building you have ever seen with your own eyes? Somewhere out there, real craftsmanship is still standing. To understand why medieval masonry succeeded, we first need to confront where modern construction went wrong. Why do brick walls built with advanced tools and technology begin to deteriorate so quickly? The issue isn't one isolated mistake. It's the failure of an entire system, built on assumptions that turned out to be dangerously flawed. And it all begins with the mortar holding the bricks together. For more than a century, construction has relied almost exclusively on Portland cement. Invented in 1824 and widely adopted during the Industrial Revolution, it was seen as a breakthrough. It hardened quickly, reached impressive strength, and could be produced cheaply at massive scale. From an economic perspective, it was perfect. Faster construction meant lower labor costs and higher profits. Strength became the ultimate goal. The stronger the material, the better the building, or so we believed. But that strength turned out to be a trap. Modern cement-based mortar locks bricks into a single rigid mass. The wall becomes a stiff slab with almost no flexibility. Buildings, however, are constantly in motion. Foundations settle. Temperatures rise and fall. Materials expand in summer and contract in winter. Medieval walls were designed to absorb and accommodate this movement. Modern walls are designed to resist it, and in resisting natural movement, stress builds until failure becomes inevitable. Here's the critical flaw. Portland cement mortar is often harder than the brick itself. When stress builds, the mortar doesn't fail, the brick does. This leads to cracking, fractures, and the familiar sight of brick faces breaking apart. This phenomenon, known as spalling, causes the outer layer of the brick to flake or burst away, exposing the softer core beneath. You've seen it countless times, walls that look diseased, scarred, and prematurely aged. But structural rigidity is only half the problem. Water is the real enemy. Medieval builders accepted a simple truth: water will always find its way into a wall. Their systems were designed to manage moisture, not fight it. Modern construction takes the opposite approach. It tries to seal walls completely, creating what it assumes is a waterproof barrier. Portland cement mortar plays a major role in this illusion. It is dense, hard, and largely impermeable. At first, that sounds like a good thing. But no barrier is perfect. Tiny cracks form, sealants fail, moisture sneaks in. Once inside, the impermeable mortar traps it. The wall cannot breathe. The water has nowhere to escape except through the brick itself. As moisture migrates outward, it carries dissolved salts naturally present in brick, and especially in Portland cement, which is highly alkaline. When the water reaches the surface and evaporates, it leaves behind a white powder known as efflorescence. While sometimes dismissed as cosmetic, this residue is a warning sign. It means the wall is saturated and unable to dry properly. Even worse is what happens beneath the surface. When salts crystallize inside the brick instead of on the surface, a condition called cryptofluorescence occurs. As salt crystals grow, they exert immense internal pressure. The brick begins to tear itself apart from the inside. Faces pop off. Entire sections disintegrate. The wall is being destroyed by the very materials meant to protect it. Studies have shown that the pressure created by crystallizing salts can reach between 2,000 and 3,000 pounds per square inch, enough to exceed the strength of many construction materials. The brick doesn't just crack, it explodes. There is another phenomenon that worsens the damage: capillary action. Brick walls can draw moisture upward through microscopic pores, much like a tree pulling water from its roots. This process, known as wicking, can transport moisture over astonishing distances. In walls sealed with impermeable mortar, that water rises but cannot escape. It accumulates, pressure builds. Over time, the force of trapped moisture becomes catastrophic. Hydrostatic pressure inside a saturated wall can exceed 3000 psi. At that point, failure is unavoidable. Medieval lime mortar avoided this entirely because it allowed moisture to evaporate evenly across the wall. Water entered, moved, and exited without causing damage. No pressure buildup, no destruction. The bricks themselves also play a role in this. Failure. Modern bricks are designed for efficiency and uniformity. They are machine extruded into perfect shapes and fired at extremely high temperatures, often exceeding 1100 degrees Celsius. This creates a dense, hard, and less porous brick. While this may seem like an improvement, it introduces new vulnerabilities. High temperature firing vitrifies the brick, making it almost glass-like. This reduces porosity but increases brittleness. When temperatures change rapidly, vitrified bricks crack much like glass, exposed to sudden heat. Medieval bricks, fired at lower and more varied temperatures, retained a porous crystalline structure. They could expand and contract naturally without fracturing. Ironically, modern bricks are more vulnerable to the freeze-thaw cycles of winter than their medieval counterparts. Water enters microcracks, freezes, expands, and breaks the brick apart. Over time, entire walls degrade. The result is a system that actively works against itself. Hard, brittle bricks are bound together with even harder, impermeable mortar. The wall becomes rigid, sealed, and unable to respond to movement or moisture. Often, this wall is nothing more than a thin veneer attached to a structural frame. Unlike the thick, solid masonry walls of the past, this system was never designed for longevity. It was designed for speed, efficiency, and profit. Durability became an afterthought, and centuries later, the consequences are impossible to ignore. Medieval builders didn't have our machines or materials, but they understood how buildings live. Their structures weren't meant to fight nature, they were meant to work with it. And that understanding is why their walls still stand, while ours quietly crumble. What we've created in the modern age is a perfect cycle of self-destruction, all justified in the name of progress. A study conducted in 2006 examined residential buildings in Istanbul constructed during the 1970s. After only 3 decades, 42% of them showed severe brick spalling and structural deterioration. At the same time, Byzantine buildings in the very same city structures built over 15 centuries ago using medieval methods remain solid and functional. The contrast is impossible to ignore. To understand why, we need to step into the mindset of a medieval builder. Doing so feels like entering an entirely different world. These craftsmen had no engineering software, no laboratory testing, no formal scientific papers. What they possessed instead was something far more powerful: centuries of knowledge passed down directly from master to apprentice. They didn't see their materials as lifeless products. They treated them as living partners. The remarkable longevity of medieval buildings wasn't luck. It was the natural outcome of a construction philosophy that worked alongside nature instead of trying to dominate it. It begins with the brick itself. Unlike today's standardized factory products, medieval bricks were shaped by their surroundings. Clay was sourced locally, often excavated directly from the land where the building would stand. As a result, every region produced bricks with unique characteristics. But the most important step happened long before firing. The raw clay was commonly left exposed to the elements for an entire winter. This slow, natural process, known as frost weathering, was essential. As water within the clay froze and expanded, it broke down dense clumps at a microscopic level. The clay became naturally refined, easier to work, and more consistent. Modern fast-paced production simply doesn't allow time for this kind of transformation. When the clay was ready, it was mixed with water, sometimes sand, and shaped by hand using wooden molds. This naturally produced imperfections. No two bricks were exactly the same. In today's construction industry, this would be considered a flaw. For medieval masons, it was expected. These irregular bricks were laid with thick, forgiving mortar joints that absorbed differences in shape and size. The result was not a rigid grid of identical units, but a flexible mosaic made of individual pieces working together. Firing the bricks was equally important. instead of massive industrial kilns with tightly controlled temperature. Medieval bricks were often fired in simple structures known as clamps. These were carefully arranged stacks of unfired bricks with channels at the base for fuel. The firing process was slow and uneven by nature. Heat rose gradually, igniting fuel in the clay at around 800 degrees Celsius and reaching peak temperatures of roughly 1200 to 1400 degrees at the core of the clamp. Bricks closest to the fire became very hard, while those farther out were fired at much lower temperatures, sometimes as low as 600 degrees. This uneven firing wasn't a flaw, it was an advantage. A single firing produced a range of bricks. The hardest, most vitrified bricks were used on the exterior faces of walls where weather resistance mattered most. The softer, more porous bricks were placed inside the wall, sheltered from direct exposure. These softer bricks could absorb and release moisture easily. The typical medieval brick was far more porous than a modern one. It could take in water, but it could also let it escape. It functioned like a sponge. It breathed. Modern bricks, by contrast, are dense and low in porosity. They resist water initially, but once moisture penetrates, it becomes trapped. Drying is slow and uneven. Medieval bricks were part of a system designed to manage moisture gracefully. Modern bricks belong to a system that tries to block moisture entirely, a battle that can never truly be won. Construction methods completed the system. Medieval builders constructed thick, solid walls made of multiple layers of brick. Where modern buildings often rely on a thin brick veneer, medieval walls could be 2, 3, or even more bricks thick. These walls used sophisticated bonding patterns such as English and Flemish bonds. Bricks were laid both lengthwise and end-on, with header bricks running through the full thickness of the wall. These headers physically tied the layers together, creating a single, massive structural unit. This wasn't decoration. It was engineering hidden within craftsmanship. The English bond, in particular, is considered one of the strongest brick patterns ever developed. By alternating full courses of headers and stretchers, it ensured that every section of the wall was locked together. The result was extraordinary stability and resilience. But the true genius of medieval masonry lay in the mortar. If the brick was the body of the wall, lime mortar was its lifeblood. The transition from soft, breathable lime mortar to rigid Portland cement is arguably the single greatest reason modern masonry fails so quickly. For thousands of years, lime was the primary binding material. It began with limestone, which was burned in a kiln to drive off carbon dioxide, producing quicklime. This quicklime was then slaked with water, transforming it into a soft, workable paste. Unlike modern cement, lime mortar didn't harden instantly. It cured slowly by absorbing carbon dioxide from the air, gradually turning back into limestone. This slow process created a mortar that was flexible, breathable, and self-healing. Tiny cracks could close over time as lime migrated and recarbonated. Movement was absorbed, moisture was managed, and stress was relieved. The wall didn't fight nature. It adapted to it. And that is why so many medieval structures are still standing today. This creamy, buttery substance known as lime putty was then blended with sand to create mortar. On the surface, it seems like simple chemistry, but this is where medieval brilliance truly begins. Once lime mortar is placed into a wall and exposed to air, it starts a slow transformation called carbonation. So over weeks, months, and even years, the mortar gradually absorbs carbon dioxide from the atmosphere. Little by little, it turns back into limestone, the same rock it originally came from. This closed loop is known as the lime cycle, and it is one of the most elegant material processes ever developed by human hands. Here's something medieval builders understood that modern construction has almost entirely forgotten. Lime putty improves with time. Medieval masons often stored their lime putty in covered pits for months, sometimes even years, before using it. During this aging period, calcium hydroxide continued reacting with water and trace amounts of carbon dioxide, forming an ultrafine colloidal structure. The longer the putty matured, the smoother it became, the easier it was to work with, and the stronger the final mortar would be. Historical records even mention lime putty aged for 5, 10, and occasionally 20 years. Today, mortar is mixed and used the same day. Quality was sacrificed for speed, and speed was renamed efficiency. The mortar produced through this ancient process was fundamentally different from modern cement-based mortar. First, it was intentionally soft. Medieval bricks themselves were relatively soft, so lime mortar acted as a perfect companion. It behaved like a cushion, absorbing movement as buildings settled, shifted, and expanded with temperature changes. Portland cement, which can be several times stronger than the brick, resists movement instead. That resistance concentrates stress and leads directly to cracking and failure. This leads to one of the most intelligent principles medieval masons followed. A mortar was meant to be sacrificial. It was deliberately weaker than the bricks surrounding it. When a wall moved, when moisture penetrated, or when centuries of wear took their toll, the mortar would fail first, not the brick. This was no accident. Repointing mortar joints is relatively easy and inexpensive. Replacing damaged bricks is costly, difficult, and often structurally risky. Modern construction reversed this logic. Portland cement. Mortar is stronger than the brick itself, so when stress occurs, the brick breaks. We created a system where the most valuable component is the one that fails first. It's like designing a chain where the weakest link is exactly the one you cannot afford to replace. The second, and perhaps most important, property of lime mortar is its porosity. Lime mortar is highly breathable, meaning water vapor can pass through it freely. This vapor permeability is the secret behind medieval masonry's incredible moisture control. Water entering the wall is not trapped. Instead, it travels through the interconnected pores of the bricks and mortar joints until it reaches the surface and safely evaporates. The wall is constantly breathing, maintaining balance without pressure buildup. Portland cement blocks this process entirely, trapping moisture inside the wall and setting the stage for decay. But the most astonishing quality of lime mortar is its ability to heal itself. This is not folklore or romantic exaggeration. It is a documented chemical reality. Over time, tiny microcracks naturally form within the mortar. When rainwater enters these cracks, it dissolves some of the free calcium hydroxide still present in the lime. This calcium-rich water moves deeper into the cracks. As it sits there, it absorbs carbon dioxide from the air, restarting the carbonation process. New calcium carbonate crystals begin to form, slowly stitching the crack closed from the inside. This healing does not happen instantly. It may take weeks or months, but it happens continuously, silently, and without intervention. While seasons change, while buildings settle, while centuries pass, the mortar is constantly repairing itself. It is like having countless microscopic workers performing maintenance day and night for hundreds of years, without cost or supervision. Modern cement offers no such forgiveness. Once it cracks, the damage remains forever. And medieval builders didn't stop there. They inherited an additional secret from the Romans that made lime mortar even more remarkable. Finely crushed brick dust, known as Hagia Sophia by the Romans and Horasan in parts of Turkey, was mixed into lime mortar. This brick powder contained silica and alumina, which reacted with the calcium hydroxide in the lime. The result was a pozzolanic reaction that formed calcium silicate hydrate, the same strength-giving compounds found in modern concrete. The difference was crucial. This ancient mixture gained hydraulic properties, allowing it to set in damp conditions while still retaining lime's breathability and flexibility. Strength was added without sacrificing resilience. Moisture could still move, cracks could still heal, the wall became stronger without becoming brittle. What medieval builders created wasn't primitive. It was sophisticated, balanced, and deeply intelligent. They didn't try to overpower nature. They worked with it, and that is why their walls are still standing, quietly breathing, quietly healing. Long after ours have begun to fall apart, it could even harden beneath water. One of the greatest examples of this is the Hagia Sophia in Istanbul, completed in the year 537 AD. Its vast domes were built using lime mortar mixed with crushed brick. A study published in the Journal of Archaeological Method and Theory confirmed that these Byzantine brick-lime mortars achieved exceptional strength and durability due to the formation of amorphous hydraulic compounds where the lime and brick particles met. 15 centuries later, after earthquakes, invasions, and the slow grind of time itself, the structure still stands. The cathedral has experienced significant structural movement over the centuries. Large-scale deformations are visible, yet catastrophic collapse never occurred. The reason lies in the mortar's long curing process and its ability to absorb and dissipate energy rather than resist it rigidly. Porous bricks combined with soft, breathable, self-healing lime mortar formed a fully integrated whole. It was a system designed with humility, one that recognized the power of nature and chose cooperation over domination. So if medieval construction methods were this resilient, why did we abandon them? The answer has nothing to do with performance. It has everything to do with economics, industrialization, and changing priorities. It is the story of how we exchanged durability for speed. The decline of lime construction began in the 19th century during a period of rapid urban expansion. Cities were growing faster than ever before. Traditional building techniques, dependent on skilled craftsmanship and slow-setting materials, struggled to meet demand. Lime mortar, for all its benefits, cures slowly. Deep joints can take months or even years to fully carbonate. The industrial age had no patience for that. Time became money. In 1824, an English mason named Joseph Aspdin patented Portland cement. Its qualities were perfectly aligned with the needs of an industrial society. It set within hours and reached high strength quickly. Buildings could be completed faster, labor costs reduced, and schedules compressed. Even better, it could be manufactured cheaply and consistently on a massive scale. At first, Portland cement was added in small amounts to lime mortar to accelerate setting time. But as the century progressed and the philosophy of stronger, faster, cheaper took hold, cement content increased. By the mid-19th century, traditional lime mortar had been almost completely replaced in new construction. An entire generation of builders grew up without knowledge of lime. Ancient wisdom faded into obscurity. This shift coincided with changes in brick production. Demand for uniformity and speed gave rise to machine-made bricks fired at extremely high temperatures. These bricks were hard, dense, and precise, perfectly suited for thin cement joints. Lime mortar, with its slow-curing and forgiving nature, was seen as inefficient and unprofitable. It was replaced by a system of rigid, brittle components assembled at record speed. The consequences were not immediately apparent. New buildings appeared solid and modern, but they began to age in ways older structures never had. They cracked. They trapped moisture. They couldn't flex or heal. Economic incentives favored low upfront costs over long-term resilience, and this flawed approach became the global standard. We became experts at constructing buildings that were never meant to last and convinced ourselves this was advancement. Yet the evidence tells another story. The decaying brickwork of a 20-year-old building and the enduring presence of a 700-year-old cathedral reveal what we lost. Today, we are surrounded by structures that age prematurely, collapsing under the weight of our own supposed ingenuity. We have mastered the creation of materials stronger and harder than anything before, yet we have built a world that is surprisingly fragile. The paradox is this. The secret behind medieval masonry's 1,000-year lifespan was its weakness. Soft lime mortar allowed movement. Porous bricks allowed breathing, slow chemistry allowed healing. Every component worked together in balance. Modern construction is the opposite. Isolated materials are locked in conflict with each other and with the environment. We traded a flexible, breathable system for the illusion of strength and impermeability. We traded endurance for short-term profit. There is one final irony. Medieval buildings didn't just last longer. They created better spaces to live in. Thick, breathable walls naturally regulated temperature and humidity, forming stable indoor microclimates. In summer, walls absorbed moisture and cooled interiors. In winter, they released it slowly, maintaining comfort. Modern buildings, with thin sealed walls, rely on air conditioning and dehumidifiers, consuming energy constantly to do what medieval walls achieved naturally and freely. We didn't only build structures that fail sooner. We built ones that cost more to inhabit every day of their shortened lives. But this story doesn't have to end in loss. Medieval knowledge is not gone, it is being rediscovered.